seven segment display. For the 7 segment display schematic diagram, this is our FDM board, and this is our switch, and this is our 7 segment. So this is our PDD, we add it as our input, and PDC, we set it as our output for 7 segment. Next, about for our segment, this will display from 0 to 9. From 0 to 9. And then this is our internal 7 segment schematic diagram, which we set it 0 to add as input, which connect to ground. Okay, let's see our programming code. First of all, we define the 7 segment and switch input, which our input, and define and define A to G, and then this is our function. It's a design. This is our function first. This is our main function, and then for the initialization call part for our function, first we enable the port D and port C, and then we set PCR for port D pin, which PE, PS we pull down because it's active high, and then we set PCR for port C for the SE, which is light out the LED 7 segment, and then we set the port data direction 1 for output, 0 for input. This is input, 7 segment is output. Next, we pass to code.
Hi, I'm Kong, and we are from group 22. So I'm going to explain the another half of the coding. So let's come for the coding. So just now we have explained that the initialization for the coding. So I will now explain the infinite loop, what's happened inside the infinite loop. Inside the infinite loop, we have two functions, read input and set digits. So read input is the reading of input from the board itself, and the coding is here. So we said that result is actually equals to PDIR and the switch input. So from what we have, we will provide a 4-bit input into the system, and it will generate from 0000 to 1111, which is 15. So with that, we can actually utilize the 0s to 9 for our LED display. So returning the result back to the main function, we will pass the LED num to the set digit, and the set digit will be as following. So as I said just now, from 0 to 9. So if it is 0, I will open up the port according to ABCDEF. So now the ABCDEF is actually declared from here. A is pin 6, B is pin 5, pin 4 for C, and until G will be pin 0. This is actually following the pattern from here. So as our LED is 7 segment, we actually have A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7. We have 7 pins here, where from port PTD0 for G to PTC0 for port G, and then to PTC6 for pin A. So come back to the coding. So with this, we can utilize each of the pin by using the OR function, and watch out for the invert here, which we change all of the pin to 0 instead. This is because for our LED, for our 7 segment, we will provide VCC as a common cathode, and we should provide 0 as the output for it to work, because 0 will act as a ground, as mentioned earlier. So with that, I control 0, 1, 2 until 9. But of course, because it's a 4-bit, so after 9 we have 10, 11 until 15. So else I will off all of them by providing ones to all the pins. So, and that's all from the coding. So now let's come to the display itself. So as you can see, this is the 7 segment showing zeros. We have 4 inputs. So 1, 2, 4 and 8. So 0 is because none of them are connected to the VCC. Now this is 1. This is 2. 3 would be 1 and 2 together. 3. We have 4. 5 would be 4 and 1. 6 would be 4 and 2. Then 7 would be 1, 4 and 2. 7. Now we have 8. And lastly, we have 9. So this is 9. So what happens when it goes tens? All will be light off. So same thing to go with 8 and 4, let's say for 12, it will light off as well. And this is it. Thank you very much. Hi, I'm Kok and we are from group 22. We are now doing the Lab E3 ADC. ADC is analog to digital converter. So for the coding, the important thing for the first thing will be the channel. We are using channel 19 for our light sensors. Other than that, we initialize clock using SCGC 6 instead of SCGC 5. We initialize the ADC by using these sets of coding. Another thing that we done was calibrating the ADC, which is using this function. So we have all sort of calibration from configuration 1 to SC3, SC2 and so on. So the important thing in this ADC is the conversion, data conversion. So as you can see here, we first declare SC1A. So the ADC 0 SC1A, we will declare it and set for the AD analog digital channel to the light sensors just now, which is channel 19, hexadecimal 13. So while CO mask is 0, so CO mask is the conversion complete. So 0 means it's not complete. So while it is not complete, wait until it completes. After it completes, we save by using the ADC 0_RA. We save the data into the result and pass it back to our main, saving at ADC data. So why do I do this conversion is because we set that the DIFF mode is 0 and we set the ADC mode to be hexadecimal 20. So hexadecimal 02. So hexadecimal 02 is the combination of 1 and 0, which is here, if you can see. So DIFF is 0 and then 10 is single-ended 10 bits. So single-ended 10 bits, the maximum will be 1023, starting from 0 to 1023. So by doing this conversion, since the voltage is 0 to 3.3 and we are not allowed to use float or double for the voltage itself because we want to avoid the floating point. So, and with that we also include a light intensity, so the more the light, the higher the intensity. So we use 1023 minus ADC data because from the data conversion, what happened is that the more light, the lower the reading. So in order to invert it, to show that the light intensity is high, we use 1023 to minus the ADC data. So let's come to the debug part. So this is the freedom board that we have. So this is the freedom board. The photoresistor will be somewhere here, and you can see through the terminals. So right now we have a reading around 150 something, and I have a torchlight here. As you can see at here, the more light I give, the higher the light intensity. Like this. So the higher the light intensity, the lower the voltage that is being given out, and it can be changed and detect if you see at the screen. And that's all. Thank you. Hey guys, there's a small change of coding from what I had previously, and this is the new coding that I use. So what happened is that voltage, the previous method was not precision enough, as I converted directly to the integer voltage. As you can see, what happened is that the digits after the second decimal place is ignored, so rounding up and down wasn't being made correctly. So in this case, instead of times 330, we times with 3300, which have 4 significant figures in this case. So after we get the data, we compare the last digit, whether is it greater than 5 and less than 9. If it does, it will be rounding up for the second last digit, which is the third digit. Otherwise, when it is 0 or the maximum to 4, then we straight away use the second last digit as our voltage 2. And here the only changes made was, instead of voltage divided by 100 for the first one, we divide by 1000, and corresponding second digits for the first digit right after the decimal will be voltage divided by 100. And last but not least, the voltage 2 that we get from this checking if else statement, we straight away put it as our final digit for the decimal place.
I would like to talk about Lab 3, Part 3. Lab 3 is talk about the combination of Part 1 and Part 2. The only difference for this is the ADC conversion is provided to rate input. Okay. And then we set the new data equal to data multiply 10 divided by 1023. This is the same concept as previous, and we set the result equal to 9 minus new data percentage of 10. So it will take the result from 0 to 9 only. Then we pass it to set digit function, and for the function is same as the That one concept. Part one concept.
And right now we will continue with the previous explanation of 1023 minus ADC data, which is for the light intensity. So since we are doing the more the light intensity, the higher the reading. So right now at the normal light intensity, the room light intensity, it will be 1. So if I block the light, you can see that it becomes 0, 1, 0, 1. So with another extra torchlight, we can control from 1, 2, you can see 2, 3, 4, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, just a little bit, 2, and 1. And that's all. Thank you.
Hello, I would like to talk about that challenge part. For the challenge part, we should enable the hardware evaluation. The coding is like this. Okay, let's see our coding. Okay, we can see that it will more stable. Like for 1, 2, 3, 4, 5, 6, 7, 8, 9. It will more stable than previous. Right? Okay, thank you.